the seminar today. Oh. So thanks so much. And it's especially meaningful, I guess, because as you pointed out, I just recently, in the past year or so, moved to Canada, and moving in the middle of a pandemic has been a little tough, let's say, at times, to kind of, figure out the community and who's who in the particle physics scene. So it's really nice to have this opportunity to kind of introduce myself to some of you today. I'm going to tell you about this really, in my opinion, really fun idea, making dark matter out of light. I work on a lot of other stuff as well, but I think this topic, well, first of all, I think it's just really fun. And second of all, given the audience today, as you'll see during my talk, this mechanism for making dark matter has a lot of really testable implications for terrestrial experiments, and in particular direct detection experiments. So before I get started, I want to give a shout out to my really excellent collaborators, Tong-Yan Lin and Cora Dvorkin, who worked on this idea with me. Okay, so all right, let's get into the science of it. So I think we can all agree with this statement, which is that dark matter exists and is dark. But there's an asterisk that I put here on the word dark because, from a very kind of empirical, experimental point of view, this is a statement that we can only ever put some sort of upper bound on. So it could be that dark matter interacts a little bit with light and been able to observe it yet. And as we'll see in this talk, that's not only a possibility, but it's one that is can really change the game. Okay, so but we know that dark matter exists. We have a ton of astrophysical and cosmological evidence for this statement here. Just recapping a few of my favorite examples. We have things like merging galaxy clusters, where this is the aftermaths of two galaxy clusters that have passed through each other. And we're seeing in pink where all the regular matter is. That's all the kind of hot plasma that, through the collisions as this merger was happening, two blobs of plasma were slowing each other down due to collisional interactions. And then meanwhile, the stuff over here in blue is where all of the matter in this picture is, as inferred by gravitational lensing, so galaxies in the background. And the important point to note here is that the blue stuff where all the matter is and the pink stuff where all the baryons are, those are offset from each other. So whatever microphysical sort of scattering mechanism was responsible for slowing down these two blobs of plasma as they pass through each other, those mechanisms were not present for whatever this blue stuff is. So from this picture, we can actually tell that whatever the dark matter is, we know that to good approximation, it's fairly inert, it's not collisional, it's just passing through itself and through the baryons, and it's not being slowed down by any sort of viscosity or any sort of drag. Okay, to good approximation from what we can tell in this picture. So that's kind of cool. Going to larger scales, we look at the cosmic web of large scale structure. We see that things are pretty clumpy. And it turns out that if you actually have a cosmology without dark matter, things don't tend to get as clumpy. Things don't cluster as well when they're only made of baryons. And that has to do with the initial conditions of how clusters and how large scale structure forms. You really need the dark matter to start to collapse first, and then the baryons fall into it at a later time. And the reason for that is because at early times, the speed of sound in the universe is really high. So if baryons try to collapse, they're going to just be washed out by sound waves. And that's a picture that's also seen here when we go to even larger scales and look at the cosmic microwave background, or CMB. And we look at these ripples. This is the afterglow of the Big Bang. We look at the ripples and we see evidence for these acoustic waves that I mentioned. And those acoustic waves, I'll get into this a lot more later in my talk, but that's the result of ordinary matter, so baryons and also photons, trying to clump together, but it's not able to because the speed of sound is really high. So there's acoustic waves that are kind of, having competing effects between compression and rarefaction. But in these sound waves, we see evidence for a component of matter that does not experience this speed of sound. It's basically just able to cluster, and we think that's the dark matter. And that is necessary to explain these acoustic waves and to later on seed the growth of structure. So we see all this great evidence for dark matter in astrophysical and cosmological systems, but this is a particle physics talk. And so we really want to know what is this stuff? What is it made of? How does it interact? And how does it fit in with the broader picture of particle physics that we have, for example, the existing framework of the Standard Model? And again, from a very empirical point of view, we actually don't have such a great grasp on this question. For example, if I just assume that dark matter is one thing, which is already a pretty strong assumption, then its mass is actually uncertain to over 90 orders of magnitude. And here in this kind of cartoon diagram, I've tried to shade in different qualitatively different sort of theories of dark matter and different regimes. At the very high mass end, we have dark matter candidates that are not even made of particles. They're most likely made of some sort of compact object or primordial black holes. We have kind of in the middle, we have this traditional set of particle candidates over here. And then moving down to even lower masses, over here, we have dark matter that is so light, and so it has to be a boson because of the Pauli exclusion principle. This is this Tremaine gun bound. And so it has to be a boson, and bosons, when you have a very high number density or a very high occupation number, they start to obey the classical equations of motion, similar to like Maxwell's equations for photons. And so dark matter in this regime starts to behave like a macroscopic wave, which is pretty different from the particle candidates. Now there's a huge diversity of different theories of dark matter here, can be very daunting, which is why in my group, I like to take the approach of saying, well, we have all these theories of dark matter. I'm going to keep that on my x-axis over here. But on the y-axis, I'm going to now look at scales where we can test these different theories of dark matter. And in my group, this is like maybe by way of introduction, so you know a little bit more about me and my group, we're just trying to fill in as much of this space as possible. So really using the whole lever arm of all these different kind of systems that the universe has provided for us, including things that we can build in the lab to test as many theories of dark matter as possible. So that's kind of like my whole vision or my whole approach. But coming back to the science, so there's a lot of different possibilities. I can't really touch on all of them today in my talk. So I want to just do a couple of things. First, I want to review the status of WIMPs, and then I want to talk about a different kind of candidate so that I can compare and contrast. Okay, so first we're going to talk about WIMPs. This is something that I know that people in the audience are very familiar with, but I want to recap it a little bit just because I want to make sure we're on the same page, and I want to share my perspective on this question so that we can, again, compare and contrast between different theories of dark matter. Okay, so we're going to just quickly go through why it is that we've been studying WIMPs. And to my mind, one of the best reasons is this really nice picture of thermal freeze out. So in the early universe, if you go to really, really early times or really, really hot temperatures, which corresponds to the left-hand side of this plot, then if dark matter is able to scatter with the standard model, it's going to come into a thermal equilibrium with the standard model. And so at early times, it's going to have an equilibrium number density. It's going to scale like temperature cubed. So now if I write my densities in a funny way where I've scaled out the expansion of the universe, because temperature scales like 1 over the size of the universe, that means that at early times or high temperatures, the co-moving density of dark matter, or for any thermal particle for that matter, is constant. But that doesn't last forever because the universe is expanding. So A gets bigger, the scale factor gets bigger, so the temperature starts to go down. And when that starts to happen, at some point, the temperature of the universe is going to become comparable to the mass of my particle that's in equilibrium. And so for any particle in equilibrium, once that starts to happen, you start to ride this Boltzmann exponential suppression curve down, like here. Okay, so you go from being in thermal equilibrium where it's constant, and then you start to be e to the minus mass over temperature. So if there's some kind of process over here, which can keep the standard model in equilibrium with the dark matter through, let's say, annihilation, then this reaction is going to proceed in the forward direction, and there's not going to be some compensating back reaction to make more dark matter. You're going to deplete the dark matter. But then again, this also doesn't persist forever. Things don't stay in thermal equilibrium forever. At some point, you've depleted so much of the dark matter, and it becomes very, very hard for dark matter particles to actually find each other to go through this process and actually annihilate. And so that process becomes very, very inefficient. And once that happens, then your co-moving number density once again becomes constant. Okay, and so this is just the general mechanism, thermal freeze out. And if you plug in a weak scale mass, so something of order 100 GeV, and you plug in a weak scale cross section, then this whole story out pops the density of dark matter that's very comparable to what we observe, which is a huge coincidence because the weak scale and the weak scale cross-section are completely unrelated to our measurements of the dark matter density, which are completely empirically determined. Okay, so there's a huge coincidence. It didn't have to be that way. These different shaded bands correspond to what would have happened if you had changed the cross-section by an order of magnitude. You would have potentially overclosed the universe. So we would not even be here discussing this. And so that really is a huge coincidence of scales. So that's, I think, to my mind, one of the best reasons why we've been focusing on WIMPs. We have this huge coincidence here. And aside from that, the thermal freeze-out story has a lot of nice properties that would be helpful for scientific theory to have. So first of all, it's very insensitive to initial conditions. The only requirement is that dark matter has to have some interaction with the standard model that will cause it to come into thermal equilibrium. So if there's any interaction, either, maybe the dark matter starts off not being populated, but it will be populated. The standard model will produce it. Or if there's too much dark matter, it's going to be depleted. It's going to come to thermal equilibrium through these interactions. So it's really nice from that perspective. We don't really care about what was happening during inflation or anything like that. So it's very, very general. Also, this mechanism is, fine with all of the early universe observables that we know about, as long as dark matter is heavier than a few MeV. More on that point later. And then finally, as I'm sure this audience is very well aware, the relevant couplings that set the relic abundance can be probed experimentally, which is really nice. In my opinion, actually, probably the most direct way of looking at this coupling is through indirect detection. So it's a little bit of, in my opinion, a misnomer, because in indirect detection, what you're doing is you're looking at this exact same kind of annihilation process that's responsible for setting the relic abundance. And you're looking for byproducts of that in astrophysical environments, like, for example, in the center of dwarf galaxies or in the center of our Milky Way. Okay, so if the dark matter, again, annihilates to standard model particles, depleting the dark matter number density and producing something visible, then at these low masses, we would have seen it by now, okay? So that's all excluded by searches for visible particles. At the same time, at very high masses, we have this so-called partial wave unitarity bound. So to make the amount of dark matter through freeze out at these high masses, you would have to violate partial wave unitarity. That's bad. So you're kind of left with this region over here that's not excluded. And this orange line right here corresponds to the WIMP window. That is the cross section that is basically going to give you the amount of dark matter that we observe. So anything below that means that you're going to have too small of a cross section. So you're not going to ride down that Boltzmann curve far enough, and you're going to have too much dark matter and you're going to overclose the universe. So that is also excluded down here. So we have this white region up here, which is making less dark matter than what we observe. But really concretely, if we want to have all the dark matter being made this way, we have this very concrete benchmark right here. And we're working on closing it with indirect detection, although it's a little bit futuristic. And of course, there's always astrophysical uncertainties looming. So that's a little bit challenging to deal with. At the same time, of course, we have the really rich direct detection program. Here's just kind of a summary of where things are at from the recent 2021 SNOMAS report. And this is just showing all of the great progress that has been made, as well as future forecasts for sensitivity, going down to sort of the so-called neutrino fog down in blue. And this is a really great, really complementary way, right? Because you look back over here, we're kind of looking at sort of 10 GeV and above as being allowed. And so we have really great coverage in that exact mass range from all of these experiments. But the only caveat here then is that it's a little bit model dependent. How do you equate early universe annihilation of dark matter to standard model particles? And how do you equate that with scattering on a nuclear target, which is how most of these experiments are operating in this mass range? So, for example, naive tree level scattering is excluded by many orders of magnitude by direct detection. But at the same time, simple Higgsino models remain untested. Okay, so there's a lot of model dependence. And I really think, it's people like to go around saying WIMPs are dead. Well, I don't think that's true at all, because in combination, with these two pictures, there's still a lot of parameter space left to test. Okay, so I think WIMPs are still a really great candidate for dark matter. But at the same time, there's been a big push to also go beyond the WIMP paradigm and to think about other dark matter candidates a little bit more broadly, and I think there's a number of rationales for why we want to do that. First of all, the WIMP is just one scenario, and we have this really big coincidence that I talked about, but it could just be a coincidence. And we have precedent for that in the history of particle physics. For example, Rabi famously said, "Who ordered the muon?" Because previously, before discovering it, Hideki Yukawa had predicted that there should be a particle that should be charged and it should have a mass of order 100 MeV, and that would be mediating the strong force. So when the muon was discovered, people thought that this was the particle that Yukawa had predicted. So they thought the muon was part of the whole story of the strong force. And now, of course, nowadays we know that the muon is just a heavy electron, and it was just a big coincidence that it had some of the same properties as what was expected. So it could be like that's what's happening with WIMPs. We don't know. And moreover, the WIMPs are a really nice story. It's a very minimalistic dark matter candidate. You don't need to introduce a lot of new physics. But at the same time, we know that the standard model is not minimal, right? It's got all these extra particles, like the muon, for example, that in some sense, we don't need all these particles to explain the cosmology of our universe. So, it could also be that the dark matter has more sort of auxiliary particles associated to it. And then finally, and this is, in my opinion, the best reason, we have all these great new technologies and new ideas and new observations that are going to be able to probe a bunch of different kinds of theories of dark matter. And so we had better be kind of prepared or ready for when these observations come online to interpret them and not, leave anything on the table. So with that, here's kind of like how I like to look at things, big picture. Here is how I like to think about the standard model as kind of like this Venn diagram, all of the different particles and the associated forces that those particles feel kind of as a Venn diagram. And as I sort of mentioned, we have evidence for dark matter, which lies mainly in the gravitational sector. Okay, so we've been able to infer that dark matter is there due to gravity. Okay, and it could be part of one of these bubbles, or maybe not. So I think I'm going to err on the side of saying probably not. And given all of the stuff I've been saying, all of the complexity over here in this sort of portion of the Venn diagram, I think it's highly conceivable that this dark matter maybe has its own bubble. I think that's not unlikely. So if that's the case, then we could be lucky. That new bubble might overlap with our bubble in the standard model. Or in other words, there might be some direct coupling to particles that we know about in the standard model. And if that's the case, that's really convenient because we can use that direct coupling or that portal to learn about what's going on inside of this bubble over here. This is a really active area of research that I've contributed to, and here are some examples from my work. But you could also be in this other situation where it could be a lot more pessimistic, and it could be that this bubble is sort of maximally decoupled from the standard model, and that's that's less fun. At the same time, though, because gravity is universal, couples to everything, at a very minimum, we always have a gravitational portal to this sector. And so we can use gravity to actually learn about what's going on in this sector. And so here, again, are some examples from my work, but it's a really, really broad effort throughout the community. The focus of my talk for the rest of today is going to be this kind of intermediate regime where we do have this very, very, very small coupling to the standard model. But it's going to be so small that in many cases, gravity is going to be one of the more helpful things to try to figure out what's going on. So in my talk, I'm going to focus on this kind of scenario. And the mass range I'm going to focus on is this sort of KeV to MeV mass range, which is interesting for a number of reasons I'll get into. And we're going to deep dive on this mass range, and we're going to talk about, in particular, the diverse power of astrophysical systems. Okay, so that's where we're going for the rest of the talk. So with that, I want to tell you about this really fun idea, making dark matter out of light. And this is an example of a more general mechanism called freeze-in. It's a thermal-ish mechanism, and it'll be clear in a few slides why I'm saying it's thermal-ish. But with this specific iteration of the mechanism, what can happen is that inside of a medium, photons actually acquire a large correction to their mass. They acquire a thermal mass. So in a vacuum, photons can't decay because there's literally no phase space. There's no way of conserving energy and momentum where they can decay. But that's no longer true inside of a medium. So you can actually decay to particles provided that those particles are very light and very weakly coupled. When I first learned about this, it sounded totally crazy to me. Sounded very, very exotic. I was like, I don't know about this. Are we sure about this? This is crazy. But it turns out this is a very well-studied kind of situation, and particularly in stellar astrophysics. So I want to just quickly give an example for that. So just briefly talk about white dwarfs. So white dwarfs are a type of star. They're basically just dead stars. And once they're born, they're held up by electron degeneracy pressure. And they're not doing any nuclear fusion or anything fun like that. So they're kind of born at some temperature, and then they monotonically just cool down over time. So if you look at a luminosity function, which is a plot of how many of these objects are there per volume, this is kind of what it looks like. Stars are born on this bright hot end, and over time they evolve and they move to this side of the plot, to the dimmer and cooler end. And this is astronomy numbers. So smaller numbers mean brighter and bigger numbers mean dimmer. Okay, so what you're seeing here is a compilation of a bunch of different points of data combined with the blue line, which is stellar evolution code, which agrees pretty well with the data. And this orange line here, this is actually the prediction for how this kind of luminosity function should look like if you only have surface photon cooling. Okay, so white dwarfs are very, very dense. They're very optically thick. The mean free path of a photon is very, very short inside of a neutron star. So you're not able to lose energy by emitting photons from the interior of the star, because those photons are going to immediately get reabsorbed. Okay, you're only really able to cool by emitting photons from the very most outer surface of the star. And that sort of cooling mode gives you this nice prediction here. And you can see that for most of this range of stellar magnitudes, this surface photon cooling law gives you a very good agreement with the data in this kind of range over here. But notably, there's like a dip down here where these two things don't agree. And what's going on is that down here, there's this channel where these so-called in-medium photons, these plasmons, they can actually decay to a pair of neutrinos through an electron loop. And this process is super rare. It's really, really suppressed because G Fermi is very weak and because it's loop suppressed. But this can happen throughout the entire volume of the star. So neutrinos are not trapped by the white dwarf. So neutrinos, if they're made on the interior of the star, they can just leave and they can carry away energy. So what happens then is that you lack stars over here. There's fewer of them that are hot than you would have anticipated because they're able to cool and evolve and move more quickly over here to the right-hand side of this plot. And so you're missing these stars. So this is actually a very well understood process. The results of the stellar evolution code match very well to the data. And so me and my collaborators saw this and we thought, well, that's really interesting. But where else do we have plasmas like in our universe? This is like a really cool effect. Can we use this in some other way? And it dawned on us that like actually the early universe is a very, very dense, very, very hot plasma. And so maybe this kind of effect would be important there. And that turned out to be very true. So if we take this sort of same kind of idea, and instead of just having neutrinos at the end, if we tack on dark matter, this is actually a very, very efficient way of making dark matter in the early universe, because the early universe is a very hot, very dense plasma. And there's also so many photons in our universe. So you only need a very, very small coupling to give you all the dark matter. Concretely, how you would maybe execute this or have this mechanism go through is in these models where you have a dark photon. So if you have some dark version of E&M, maybe your dark matter is charged under that dark version of E&M, and that dark photon will at some level mix with the standard model photon, sort of in a way that's similar to neutrino oscillations. It's going to happen at some level, and so that's going to give you this effective coupling between dark matter and light. And sometimes people talk about charged dark matter or millicharged dark matter as maybe one kind of candidate. And as far as I know, this is actually the simplest way of making dark matter that looks like it has an effective charge that's not ruled out. So we've been able to look for charged dark matter or dark matter interacting with light already, and we've gotten very good at that. And this is kind of the remaining way of making dark matter that's simple and that's not ruled out. So that's kind of interesting. So that's an interesting idea. You'll note that I have sub MeV in this sort of schematic diagram. Why am I focusing on that mass range? And that's because of the following reason. So sub-MeV dark matter, it's sometimes said you can't make it from a thermal process. And I'm going to just briefly walk you through why people say that. So again, here's a plot of the number density and units of the relic number density, or it's a co-moving number density. And again, at early times is constant. You have this Boltzmann e to the minus mass over T phase, and then it freezes out and it becomes constant again. And if you have dark matter, that is 1 MeV in mass, this e to the minus mass over temperature starts to happen in this kind of range of temperatures. So sort of like sub-MeV temperatures. And that's really bad. Okay, by the way, I think this plot looks like a dolphin. So there's the eye. I call this the dolphin plot. Okay, so on this dolphin plot, having the sort of nose coming down over here is really bad because when you have this dark matter that's annihilating and riding this e to the minus m over t curve down, that's going to be transferring a bunch of energy and entropy into the visible sector. And so if you do that, you're going to mess up. First of all, neutrinos have decoupled by that time. So if you start adding entropy, you're going to heat up either the photons or the neutrinos. You're going to mess up the temperature ratio, which we've measured using cosmology. So that's bad. Also, if you're injecting tons of energy at this time, you know, here over here at sort of like 0.1 MeV, we have deuterium is trying to form and do BBN. So if you're, you know, injecting a lot of energy, you're disrupting the formation of deuterium. That's also quite bad. You can actually mess up BBN. So for that reason, this sort of freeze out picture at this sort of mass range is excluded. Actually, the constraint is more like five-ish MeV. Okay, so anything below that is excluded. On the other hand, though, you'll see in this blue line, I have freeze-in, and that's a completely different kind of mechanism. So with freeze-in, you start with very, very little dark matter, and you make it slowly, sort of more and more over time. And in some sense, it's the opposite of freeze out. So freeze out, you start high, you go low. Freeze in, you start low, you go high. And in this sector, there's very, very little energy or entropy in this sector. So that means that as you're freezing in, you're not really disrupting any of these processes in the early universe that I mentioned. So that's actually, in some sense, a bit of a loophole. So if you're freezing in from a thermal species, so like, for example, if you're doing this plasmon decay where the photons, the plasmons are thermal, and you're making more and more dark matter over time, it's sort of a thermal-ish mechanism because the dark matter itself is not thermal, right? It doesn't have this thermal number density up here, but it's being born from a thermal process. So for that reason, freeze-in is kind of like a bit of a loophole to this statement that you can't have thermal dark matter below an MeV. And in some sense, that's partly why freeze-in is one of the sort of the main benchmarks, as you'll see in a couple of slides, for sub-MeV dark matter. So this is cool. So, okay, you might worry, well, you know, we just said this is a thermal-ish mechanism. Okay, so the dark matter can't thermalize with standard model. That better mean that the coupling had better be really, really tiny. Otherwise, it's going to thermalize, right? So that's you may worry, okay, that's never going to be detectable. It turns out not to be true because indeed the coupling, as I'll show you in one slide, is going to be really, really tiny. On the other hand, though, if you have a situation like in, for example, our galaxy, where you're looking at scattering and the typical speed is like 10 to the minus 3 times the speed of light, then processes like this one get a really big enhancement. So if you have a light mediator, like this light dark photon over here, then you're going to get a velocity to the -4 enhancement, similar to Rutherford scattering. And so that's potentially 12 orders of magnitude enhancement to the cross-section compared to what you would have had in the early universe, where things were moving relativistically in the early universe. So that's a huge, huge benefit to this kind of search. So if you have scattering searches like this one, you have a bunch of different proposed direct detection experiments that are able to target freeze-in. Okay, this is this purple line over here. This is including this dominant plasmon contribution to freeze-in. As advertised, the coupling over here is really small. So this dark matter looks like it has an effective charge that's of order 10 to the minus 11. Another way of thinking about it is like asking what is sort of like alpha, what is the fine structure constant of this dark matter? And it depends, but it can be as low as 10 to the minus 20. Okay, so this is really weakly coupled dark matter. Nevertheless, all these experiments are able to look for it using a bunch of really clever ideas that I won't summarize here in detail, but you can check out these papers over here. The key sort of, in a nutshell between all these ideas is that they're all dealing with collective effects and gap systems. Okay, so that's kind of a fun kind of almost new frontier of direct detection. But the point here is just that freeze-in, even though it's really small, the coupling is really small, you can still look for it. So I want to give just a quick recap of my talk so far before moving on to talk about the cosmology. So far what we've talked about is we talked about thermal freeze-out. We recapped why it's such a great and such a compelling thermal history, being independent of initial conditions, being testable and things like that. And so now what I'm trying to advocate for is like, if I just take this time arrow and I reverse it, then that sort of gives me freeze in. Okay, so now standard model particles are making dark matter over time. And specifically, if you have this light vector mediator and I include this plasmon decay channel, then the relic abundance is independent of initial conditions. As we kind of saw in my dolphin plot, most of the dark matter is being made at late times. So you don't actually have a lot of sensitivity to what's happening at very high temperatures or at very early times. Also, as we saw, you can go down to lower masses. So for freeze out, you can't really go too far below an MeV, but with freeze in, you can go down to actually as low as a KeV and you're still fine with all these early universe observables. And in spite of the very, very tiny couplings that are kind of keeping you from thermalizing, this is actually still a very testable idea. Okay, so that's kind of like a recap of my talk so far. And now for the remainder of my talk, I want to discuss how we can constrain this idea using cosmology. So instead of using a direct detection approach, which is highly complementary, I want to talk about cosmology. Okay, so are there any questions at this point before I move on to the latter part of my talk? I just want to make sure we're all on the same page.
I don't see any hands up.
Great. Okay, so in that case, I'm going to move on. And the key piece of insight that we're going to use, that it's going to be cosmologically relevant, is that dark matter that is born from freeze-in is born hot in a sense. And here I put quotation marks around the word hot, because as I've really tried to emphasize here, the dark matter does not necessarily thermalize with the standard model. So it doesn't even necessarily have a well-defined notion of a temperature. But nevertheless, what I mean here is that because the dark matter is being made from standard model particles, and in this case, it's decaying light primarily, you're going to be inheriting a lot of the kinematics of those particles. So if you actually go and compute in detail what the phase space distribution looks like, which we did this in our paper, it ends up looking something like this. So here's this phase space as a function of momentum, and I've written the momentum in units of the photon temperature. And the reason why I've done that is because both the momentum and the photon temperature, they scale the same way with the expansion of the universe. And so this quantity on the x-axis is redshift independent, or it doesn't matter at what time we're talking about the phase space, it's always going to look like this. And there's a few things to point out in this plot. First of all, my statement about dark matter being hot, you can see that it's true because the peak in sort of this distribution is close to peak high over T gamma equals 1. And that sort of corresponds to the momentum of the dark matter on average having order unity of the temperature of photons. So indeed, we can see that this dark matter is going very fast. In a sense, it's very hot. But we can also see that this distribution here is quite different from a thermal distribution. And so this dashed line is showing the equivalent thermal distribution that you would get if you had, this sort of same sort of p squared, so same moments of your distribution, but just reshuffling it so that you have something thermal. Okay, so this distribution is very peaked at low momenta and has this very, very high momentum tail. Feel free to ask me about that more if you're curious as to where that comes from. But one thing I do want to note is that optionally, dark matter can in fact thermalize. So if you take this initial purple distribution and you introduce dark matter scattering, that scattering can sort of shift around the momentum inside of the dark sector. So this dark matter is not going to thermalize with the standard model. So it's not going to share the same temperature as the standard model, but it's going to have its own temperature. Okay, so that can actually optionally happen. And now there are some constraints in that happening. So it can't happen at very early times. So on this plot, I'm showing the redshift at which thermalization occurs, Z therm, as a function of the dark matter's mass. And it depends a little bit on how strong you make the dark gauge coupling. So if you make the dark gauge coupling really big, you're going to thermalize at early times, but that's bad because then, I showed early on in my talk, this bullet cluster, you're going to start having too much dark matter scattering. It's going to mess up the bullet cluster. It's going to make it so that now dark matter, when it's in this two merging clusters, it's going to start behaving in a collisional sort of manner. It's going to have this effective viscosity, and that's bad. So this whole region up here is ruled out. But you can see that there are kind of these allowed regions where the dark matter can potentially thermalize pretty early on, and that's actually going to create that distribution. Regardless of which distribution the dark matter has, though, in either case, there are going to be implications for cosmology from this phase-based distribution. And that's what we explored in this latter paper. So one of the two implications is going to be clustering, velocity effects on clustering. So I'll just maybe spend a few minutes talking about what we know about this. So a good analogy can be made with warm dark matter, which is this theory where in warm dark matter, you have these initial conditions. The number density of dark matter is equal to m chi over 94 eV times this ratio of temperatures cubed. And you can see that for a fixed amount of dark matter, it's like an inverse relationship between T and m chi. So the hotter you make the dark matter, the lighter you have to make m chi, or conversely, the heavier you make m chi, the lower in temperature you have to make T chi to give you the same amount of dark matter. And so these two simulations show two sort of different masses of warm dark matter. You can see over here in the case where the dark matter is lighter and hotter, you actually sort of smear things out. You don't have as much structure, particularly on smaller scales, because what's happening is that if you lower m chi and you raise T chi, the typical velocity of a particle, RMS velocity, goes like the square root of T over m. So if T is high and m is low, then your RMS velocity is very high. And from the point of view of structure formation, that's quite bad because structures that are starting to form are very delicate. If you have stuff that would have fallen into them, but now it's moving too fast, so it's going at speeds that are above the escape velocity, then these little delicate structures are never going to be able to finish forming and finish coalescing. And what's going to happen is that if they don't accrete enough matter, if they don't gather enough stuff, they're just going to dissipate. And they're just going to be ripped apart by external tidal fields. Okay, so you're going to erase all of those structures because dark matter is going too fast and it cannot be gravitationally captured. And so these two universes look very different from one another, and we're actually very good using cosmology at distinguishing between these two universes. One of the best probes we have of this is Lyman alpha forest. This is maybe one of the most well-studied mechanisms for studying this case. And what you have here is you have some very high redshift source of light. In this case, it's usually a quasar, and it has some intrinsic broadband spectrum that looks something like this, okay? So that's what the intrinsic spectrum looks like, but then the light is traveling to our telescopes through the intergalactic medium. And as that light is actually traveling, it's passing through clumps of neutral hydrogen. And every time it passes through a clump, it's going to have some of the Lyman alpha photons being absorbed by that clump of neutral hydrogen. Okay, so that's an atomic transition. But now, as the universe is expanding, as these photons are moving, all of the spectra are redshifting. So the whole spectrum is moving to the right. And as that spectrum moves, every time you encounter a new clump of neutral hydrogen, there's some pristine part of the spectrum that does not have this Lyman alpha absorption imprinted onto it. So when all is said and done, you end up with this kind of spectrum. It looks like this over here. This is a so-called dense forest of spectral lines. And each one of these lines, each one of these absorption features corresponds to a clump of hydrogen. And given that we know the rest wavelength of neutral hydrogen for Lyman alpha photons, we can infer at what redshift was that clump of hydrogen. So along a given line of sight, we know exactly how many clumps there were at and exactly what location those clumps were. And that tells us about how much things are clumping and how structure is forming. We can actually use that to infer whether or not we have warm dark matter or regular cold dark matter. So that's one of the most well-studied ways. We also have a couple of ways that are sort of emerging or sort of newer. Basically, if you erase the smallest little structures, you're going to erase the smallest halos of dark matter. And you're also going to correspondingly erase the galaxies that would have lived inside of those halos. So if we find small galaxies that live inside of low mass dark matter halos, that means that those halos must have not been erased, and therefore you can use that to set a bound on warm dark matter or theories like it. There's a bunch of ways people have been using to look for these little small dark matter halos. They're getting more mature. And in my opinion, one of the more mature ones is this way of looking for fainter nearby galaxies. So here's just an example of a plot from the Dark Energy Survey, which is finding fainter and fainter galaxies all the time. So here's kind of a map of like all of the previous galaxies that we knew about are in these different colors here. Like blue is SDSS discovered, things like that. But all of these red galaxies over here were discovered by the Dark Energy Survey. So the more and more of these galaxies that we find that are low in mass, the more stronger constraints we can place on warm dark matter or theories like it. Okay, so that's all really been a lot of great developments on the cosmology side. We can then take that, which was sort of applied to warm dark matter and apply it to Friesen. So going back to our good friend, the phase space distribution. So we want to predict from this distribution how much suppression of structure is there going to be to clustering. And it depends a little bit on whether the dark matter thermalizes or not. If it doesn't thermalize, if it sort of retains this blue distribution over here, then it's sort of just like dark matter isn't thermalized. So it's like it just gets shot out of a cannon and never talks to anyone again. You can treat it a little bit like neutrinos in cosmology. And the exact shape of the distribution matters, but most of the suppression is going to come from this high velocity tail over here. So you can calculate that using a Boltzmann solver. On the other hand, if the dark matter thermalizes, like in this case, this distribution over here, it's a little bit different. So now the dark matter can bump into itself. It has a speed of sound that's non-trivial. And again, you have to account for that, but you can do it using a Boltzmann solver. And so we ran a Boltzmann solver on all of these distributions to calculate what kind of suppression of power are we going to get relative to cold dark matter. So that's what this ratio is. So on large scales, so here K is sort of the wave number of what Fourier mode am I talking about? And so low K corresponds to large spatial scales. And on large scales, everything agrees between cold dark matter and the situation that we're looking at. So on large scales, this ratio is 1, but on small scales, as K goes to larger values, you're erasing structure. And so now the power relative to cold dark matter starts to plummet. And the details of that depends on the theory of dark matter. So here I'm showing the constraint. So this is 6.5 keV warm dark matter. This is the sort of leading constraint from the Dark Energy Survey. It looks like this. And we can actually run our Friesen phase space through our different solvers and try to match that on to this warm dark matter case, which is excluded. And so that's what we've done here. And as you can see, it depends a little bit on the details of whether or not the dark matter, the Friesen dark matter has thermalized or not. But regardless, we can actually use these kinds of constraints on warm dark matter and bootstrap them and get a constraint on Friesen. And so that's what we did. So given these two distributions, these different kinds of probes over here can rule out Friesen dark matter lighter than roughly 17 keV. Okay, so it depends a little bit on which system you're talking about, but one nice thing about astrophysics, even though it's really messy, is that we have all these independent systems that make all these different independent assumptions or have different systematics. So that's really powerful. In the last 5 minutes or so of my talk, I'm going to discuss this other probe, which is the cosmic microwave background, CMB. And that's another actually way that we can test for Friesen dark matter by looking at dark matter baryon drag, or in some sense, we're kind of using the primordial plasma of the universe as a direct detection experiment. So trying to have dark matter ramming into particles in this plasma and seeing the recoil. So that's kind of a fun analogy. Let me tell you a little bit more about how exactly that analogy works. So here's a kind of cartoon picture of what's happening in the primordial plasma of our universe. You have some gravitational potential well, which is laid down for you by some theory like inflation or something similar, which gives you some sort of spectrum of scale invariant perturbations. And what happens is that now you have some gravitational well, and things are going to want to start to fall into it because of the force of gravity. So gravity is trying to bring everything together, but at the same time, prior to recombination, we have a very tightly coupled photon baryon plasma in the early universe. And so at some point, things are coming together due to the force of gravity, but the photon pressure, the radiation pressure, is going to become insurmountable at one point. And that's going to tend to push things apart or smear things out due to that pressure. So the photon baryon fluid is falling in, and then it's having radiation pressure, and then it's bouncing out, and it's falling in and bouncing out over and over again due to these two competing effects. But if you have collisionless dark matter in the game, that does not really experience radiation pressure. It just sort of sinks down to the bottom of the gravitational potential well due to the influence of gravity, and it just sort of stays down there. And in doing so, it affects the shape of the potential well. In some sense, you can think of it as loading down or weighing down the photon baryon fluid. So in this sort of two competing effects, the tug of war between gravity and radiation pressure, dark matter actually gives gravity a little bit of a leg up. So when we look at the CMB, we see enhancement to the compression part of these sound waves. That's actually that's one of the strongest pieces of evidence for dark matter. But if the dark matter is not perfectly collisionless, let's say every once in a while it's colliding with some of the particles in the photon baryon plasma, then once in a while, these dark matter particles are going to be pushed out of the bottom of the gravitational potential well. And so what's going to happen instead now is that you have less stuff down here. So you have less dark matter at the bottom. And so there's less stuff weighing down the photon baryon plasma. And that means that now the sort of shape of your acoustic waves is going to be modified. And in particular, if you have freeze in, like I mentioned, you have this v to the -4 scattering. And so this is the velocity details are going to really impact how much of this you get. So we have to return to our friend, the phase-space distribution, and really try to quantitatively understand that. So if you have dark matter that is thermalized versus dark matter that is not thermalized, you have different amounts of dark matter in the low velocity portion of the tail. And that low velocity portion, again, is what matters because it's v to the -4, so that the lowest velocity particles are going to dominate this story. Okay, so due to the different distributions over here, as you might expect, there's different amounts of drag between these two scenarios, between the dark matter and the photon baryon plasma. Here's one way of capturing these effects. Like you can construct something called a drag rate. That's this arc high, and you can write it in this sort of dimensionless way. So this quantity on the y-axis is dimensionless. And if it's order unity, that's telling you that things are being dragged a lot. So we can see it's kind of like at the percent level, depending on the initial conditions of the dark matter. If it's cold initial conditions, that's the most drag, because again, cold, so low velocity, that means v to the -4 is going to be the most powerful. And the thermalized case has the least amount of drag. But nevertheless, it's kind of like, it's like a percent level drag. And the CMB is really good at making sort of percent level statements. So you can translate this drag, again, by running a Boltzmann solver. You can translate this into how is this going to affect the multipoles of the CMB? What is going to be the shift? And it's sort of like over here, this is like a plot of the change in the CLs divided by the CLs. So it's kind of like a percent level effect. And so we can actually test for that. And me and my collaborators did that using existing Planck data. So with the Planck 2018 likelihoods, we actually found that freeze in below around 18 keV or so is excluded. Okay, but in the future, we're going to have a bunch of new probes coming online. So for example, we're going to have CMB stage 4, which is like this proposed experiment. And we think that given the benchmarks that have been set for that experiment, we're going to be able to exclude or to test freeze in dark matter up to roughly 28 or 29 keV. And then in the future, doing even better with other kinds of probes of clustering, similar to what I talked about, which is complementary to the CMB. So things like 21 centimeter is going to be really helpful. And also the Rubin Observatory is going to be getting us potentially all the way up to 50 to 80 keV, depending on the thermal history. So that's really kind of fun. We're really going to be able to make a lot of progress using cosmology. And I want to again remind you that this is all cosmology, but this whole shaded region is a key benchmark for direct detection in the sub-MeV mass range. So we're kind of in this exciting situation where, on the one hand, we have all of these astrophysical and cosmological probes kind of setting stronger and stronger limits coming from masses from below. At the same time, having direct detection experiments coming kind of from above and having a good amount of overlap in coverage between the two. So I think in the next couple of decades, we could either find this dark matter or we could conclusively exclude this dark matter from being the dark matter that describes our universe. And I think that's really exciting. So just to summarize my talk today, so we went over a lot of stuff, but we talked about how dark matter could be made of decaying light, which is a crazy sounding idea, but it's actually a very simple idea. It's very well understood in the context of stellar astrophysics, and it's the simplest way of making charged dark matter. We also saw it's like one of the key benchmarks for sub-MeV dark matter experiments. We saw there's this whole sort of loophole to the statement that you can't have thermal dark matter below an MeV. And that's why this is one of the main games in town. It's because it's having this loophole that it's exploiting. And then we saw how all of the funny phase space could change the cosmology of the universe and lead to sort of interesting behavior that we can then go and test. So I just want to maybe leave with the final comment, which is like our universe is a really big place. There's a lot of room for creativity. So the story that I told about, thinking about neutrinos in stellar astrophysics and then being kind of inspired of using a different plasma provided by our universe, that's actually a true story. And then we saw all the different kinds of astrophysical systems being utilized today during this talk. But there's also complementarity with terrestrial and laboratory experiments. So there's a lot of room for interplay and a lot of room for creativity. So I'd be happy to hear any comments or any questions and maybe even brainstorm ideas for collaboration down the line. So thanks all for your attention and happy to discuss. So thank you.